this is the hardware of the digital PID, and now we will operate this in the open loop condition. If we set Kp equals to 1, firstly the input to this PID controller is this 1 Hz square wave. Right now all the parameters are set to 0, that's why the output is 0. We will now set P equals to 1. Now P equals to 1 is set, the controller is running, and the input and output are coinciding. Both the waves are at 5 volts and minus 5 volts. Now when Kp equals to 2, the output is double of the input. When Kp is now 0.5, the output is now half of the input. Now we will see the integrator, the I mode. Now when the input is square wave and I value is 1, we will reset the Kp. Now when I equals to 1 and we run it, we will get a triangle wave. Now integrating the square wave will give us a triangular wave. Now if we set I equals to 2, then we can expect the triangular wave will be multiplied by 2. If we now run it, it got multiplied twice. Now we will check the derivative mode, that is the D, by varying the D parameter. Now if we clear I and then set D, and run it now, we will see spikes during the rising edge and falling edge, because the derivative tends to infinity at that point. Now if we change the wave to a sine wave, then we can see that the output is shifted by 90 degree. That is, the output is lagging by 90 degree here because of the derivative of sinusoidal wave. Now we will check the controller in the closed loop mode. Now closing the circuit, Right now we are seeing too much oscillations because the parameters are not set correctly. Now if we use the PID mode in our closed loop configuration, let's say we reset all of these. And now run it. This is the output of the plant. So we can see the PID controller gives the output which is fed to the plant, and this is the plant output. Now if we want to see the plant input, then we can see it here with a scaled down version of it. Now if we zoom in, then we can see what the plant actually gets as its input.